Good afternoon, everyone. I'm glad to be here for this conference. First, let me introduce myself. My name is Yuting. I'm a Master of Information and Communications Engineering, and I got my degree in Xidian University 2021. Today, I will share my research topic about text-to-image synthesis with generative adversarial networks. Here is the overall overview. Its backgrounds and related works and existing problems and our contributions. To begin with, I need to give you some background about it. Convolution and deconvolution operation, generative adversarial network, and text-to-image generation. I believe that most of you are familiar with the convolution operation. When we need to extract the image features, we will use this. After this operation, the size of the feature will be unchanged or reduced. It's often used in classification tasks, where deconvolution, on the other hand, can increase the size of the inputs. We can use it for feature generation and image generation. Besides, in some fields, they are combined, such as image denoising. Text-to-image generation is used for generation tasks. When we have natural networks generate images, we often have network build them up from low resolution. In order to do generation, we need to some way to go from a lower resolution image to a higher one. We generally do this with the deconvolution operation. Roughly, deconvolution layers allow the model to use every point in the small image to paint a square in the larger one. However, when we look very closely at images generated by natural networks, we often see a stranger checkerboard part of artifacts. Deconvolution can easily have a user putting more of the phantasmorical paint in some place. Fortunately, there is a widely used approach of feature generation, that is to separate upsampling from future generational computation. For example, you might use the nearest neighbor interpolation or bilinear interpolation to reset the image and then do a convolutional layer. This seems like a natural approach. So we solve the uneven overlap, which means we can have the network to synthesize image from noise vector, but we still have a problem. That is how to supervise this process. Image generation is a high-freedom task that we were not able to figure out a good way to supervise this process. Fortunately, according to Goodfellow, the generative adversarial network framework appeared as an unsupervised network architecture based on game theory. GAN makes it possible for the generator to learn the true distribution through alternative training of generator and the discriminator without knowing the real distribution of the target. Finally, the text generation is reliable. With NLP tools, the text-to-image generation task risks, as the name suggests, it makes the net generate images that match the given description. Lead first use GAN for text-to-image generation. NLP tools based on skip sort are used to obtain the future of the sentence. Skip sort follow n-grams in what-to vector use the current sentence to predict both the next and the previous. After input of the last word, the hidden states of LSTM are treated as the sentence global future. Next, I will introduce the text-to-image generation tasks from way and tab, changes and challenges between them, and my focus. There are main two methods for text-to-image generation. One is generate feature and synthesize image directly. This means model firstly gets the initial images and use it for further generation by each block. Another is generate the layout first. This is generate layout first and then use the layout for detail generation. In this way, model needs the extract task to know the instance info, like science graph, to get the layout. For tabs, There are main two types, which are single object generation, and other is multi-object generation. In single object datasets, 11,788 bird images belonging to 200 categories are contained in COB. Each images has 10 text descriptions. The description is fine-grained about object parts, color, and another things. Oxford contains 8,189 images of flower and from 102 different categories. This description is also fine-grained description. We can see stigma or other color and some description about the flower. Compared with COB and Oxford, most of the images in COCO come from life. There are many objects in the images, the tree, the dog, and the other. And the scene is more complicated. Each image has 5-sentence description. The description is briefly. There are some changes and challenges between them. First, direct generation means model doesn't need to parse how many instances there are in a sentence, while layout needs to use the preprocessing of NLP tools to know the instance information. The multi-stage model generating the image directly works similarly in each up block, and the cooperation is easier than others. Then single object dataset has a fine-grained description. However, COCO only has briefly sentence. We may focus on single object generation and do not generate layout. We hope to simplify the use of the NLP tools and focus more on the problem of generating models. At the same time, we also found through experiments that generating one layout is not less difficult than initializing one beginning image about some related works. So why is the multi-stage models? As the training process is stable, the first GAN in text-to-image only generates plausible images for birds and flowers. To reduce the instability of the training process, the following text-to-image generate methods may apply a multi-stage generator to impose more realistic. Zhang extends single stage to multi-stage in their StackGAN and StackGAN V2. The stacking structure makes the generation process more comfortable to synthesize larger images. Go one step further, the word level information can get the local generation. She introduced the attention GAN with deep attentional multimodal similarity model to refine images, which takes into account both local and global information. Nevertheless, the multi-stage structure has points and cons. On the one hand, stacking structure addresses the size limitation by means of bit-by-bit surveillance. On the other hand, if the surveillance is biased, the biased surveillance from the discriminator in each stage will be accumulated. Meanwhile, the model is prone to collapse when it is supervised by biased strong surveillance. So building comprehensive surveillance is also crucial for the model to be a success. As mentioned above, there are still 3 issues in the multi-stage structure. First, the cascade structure accumulates incorrect and redundant information during the generation process. Second, the output of discriminators is the probability, which cannot get the generator comprehensively. Finally, bad initialization of images with unclear parts made the refine difficulty. To address these issues, first, we advanced an adaptive forgetting mechanism in the generator to reduce the error accumulation and learn knowledge flexibly in the cascade structure. Besides, to evade the model cracks caused by strong biased surveillance, we propose a multitask discriminator using weak supervision information to get the generator more comprehensively and maintain the semantic consistency in the cascade generation process. To avoid the refine difficulty caused by bad initialization, we judge the quality of initialization before initialize the before further processing. The generator will resample the noise and re-initialize the bad initialization to obtain a better one. All the above contributions have been integrated into a unified framework, which is adaptive learning and generating generative adversarial networks. As we know, in the process of cognition, we ignore the redundant and incorrect information to learn and summarize knowledge more efficiently. Inspired by this, we incorporate a pair of downsampling and upsampling convolutional layers to the up block, so we can bring the forgetting process. Thus, the model has the opportunity to throw the useless and improper information away, which is called the forgetting mechanism. For the second problem, we design a multitask discriminator to fully utilize the additional weak supervision information in the training process, which can help the discriminator to get the generator in detail. For the last problem, traditional multi-stage generators start from the initial images to synthesize the larger one, regardless of quality of them. However, people do not prefer this way. We often say that good paintings usually start from a satisfied draft. Therefore, we propose to supervise the generation process of a small image to guarantee its quality. This is called drifting mechanism. During the training process, we will train the model. Firstly, the input text description is transformed by a text encoder into a word-level representations and a global filter. The global filter is used as the sentence condition. Then the initial generator predicts the roughly sketch of image according to a random noise vector with the sentence condition after conditioning argumentation, and the noise vector is normally distributed. After initialization, more fine-grained visual contents are supplemented to the initial image by attention-based upblock, which makes it more photorealistic. Because of the limitation of GPU, we applied the upblock twice to get the image with resolution of 256 figure only draws the upblock once. The traditional text-to-image discriminators distinguish not only the real data from synthesized images, but also the matched sentence conditions from mismatched conditions. However, that is a biased surveillance. In our multitask discriminators, the discriminators have an auxiliary task for predicting weak supervision information on the synthesized and the real data. By predict the information, discriminators can give comprehensive surveillance from category or attributes rather than a biased one probability. We proposed, process and split the image into two disjoint sets following the same pipeline in Leeds method, 150 categories with 8,855 images training, while the remaining 50 categories for testing. We choose the category and the fine-grained attribute annotation as the weak supervision information and figure out the effectiveness for each of them. Oxford 102 different categories, 18 to categories with 7,034 images for training, while the remaining 20 categories for testing. It only has category annotation, so we employ it as the weak supervision information. About the evaluation metric, we use Inception Score and Fréchet Inception Score as the quantitative evaluation methods. Inception Score measures both quality and diversity of generated images. It computes KR divergency between the generated data class distribution and the real data distribution, which use the pre-trained Inception V3 nets. A higher score means a better performance. Fréchet Inception Distance computes the Fréchet distance between generated images and the real images using the extract features from the pre-trained network. A lower FID means a closer distribution between generated images and the real ones. We compared our results with the state-of-the-art text-to-image methods on COB and the Oxford datasets. Report the results of Inception Score here. It is confirmed that our model can generate images with better quality and diversity. Then we discussed the effectiveness of new generating process. We refined the images before and after drifting mechanism. It can be said that the images quality after drifting mechanism is much better than before. The flower is more clear and the bird is more, the structure of the bird is more clear and have not the modal crops. This is mainly because some unclear parts may appear during initialization. Having such a part will confuse following block. Representative examples generated from text description by different methods are shown here. Compared with each others, the images generated by our model show the bird structure more clearly, which is related to the high quality initialization. At the same time, in our results, the bird's further texture is more natural, which means the model receives more specific guidance. In addition, the learning process with forgetting is more natural. To further demonstrate the effectiveness of each component, we perform some ablation experiments. Here are the results. The results demonstrate that each component in our model is indispensable. About the forgetting mechanism, based the baseline, it improved Inception Score over 1% over the baseline on COB, where it resulted in over 3% improvement on Oxford. To avoid the impact on the model due to the increase in the amount of calculation, we test the model with a normal convolution 3x3. This confirms that forgetting the redundancy information benefits the generator. Multitask discriminator. Based on forgetting mechanism, we further evaluate the effectiveness of multitask discriminator. When the discriminators conduct the category classification task, it improves Inception Score on COB and Oxford. When the discriminators conduct the attribute classifications task, it also improved as on COB. The improvements prove that the weak supervision of discriminators gets generators in a comprehensive way. Besides, the more fine-grained the guidance is, the better the quality will be. Finally, it's about something future work. Text-to-image generation is a cross-domain task. Now we can make the network draw with the cross-domain knowledge. We can go further to make the network do a zero-shot work or generate some videos. However, all of these are applications. They are indispensable from better text processing tools. So we also need more powerful NLP tools. That's all. Thanks for your listening. I will be pleased to answer any questions you may have.